Over 500 new FRBs detected in single year due to CHIME telescope. Fast radio bursts, or FRBs, blaze for a few milliseconds before vanishing without a trace. Their origins are unknown, and their appearance is unpredictable. In the decade following their discovery in 2007, only 140 FRBs had been seen. Now, thanks to the launch of a large stationary telescope in the interior of British Columbia in 2018, the number of new FRBs detected has almost quadrupled, for a total of 535. Moreover, a McGill-led inter-university collaboration has put together the first CHIME FRB catalog, which will be presented this week at the American Astronomical Society meeting. CHIME is unique in that it observes the entire northern sky once every day. Signals from over 1,000 antennas are digitally processed in real time to enable high-sensitivity measurements over a wide range of frequencies. It is already yielding clues about the properties of FRBs. For instance, there may be distinct types of FRB events, based on the shape of the burst and the range of radio frequencies it comprises. Different astrophysical qualities underlying different classes of FRBs? Among the 535 FRBs in the new CHIME FRB catalog, scientists have identified 18 FRB sources that burst repeatedly, while the rest appear to be one-offs. The repeaters also look different, with each burst lasting slightly longer and emitting more focused radio frequencies than bursts from single, non-repeating FRBs. In some cases, it takes thousands of hours of observations to detect a single burst from some FRBs, while others have repeated within the span of tens of hours, says Pragya Chawla, a PhD candidate in the McGill Physics Department. Our current sample indicates that there are significant differences in the properties of repeaters and non-repeaters, and future studies will allow us to determine whether the two kinds of events are generated by different astrophysical phenomena. FRBs may be distributed across the sky from the FRBs that CHIME has detected. The scientists have calculated that bright fast radio bursts occur at a rate of about 800 per day, the most precise estimate of FRB's overall rate to date. When they started mapping the locations of the FRBs seen between 2018-2019, the researchers found that the bursts were distributed uniformly across the sky, suggesting that the FRB population is spread throughout the universe and not located simply in our Milky Way galaxy. For each of the 535 FRBs that CHIME detected, the researchers measured its dispersion, and found that most bursts likely originated from far-off sources within distant galaxies. The fact that the bursts were bright enough to be detected by CHIME suggests that they must have been produced by extremely energetic sources. With more observations, astronomers hope to pin down the extreme origins of these curiously bright signals soon. FRBs also carry information about the medium that they travel through, adds Saurabh Singh, a postdoctoral researcher in McGill's physics department. With the significant increase in their detections over a range of distances from us, they potentially offer an independent measurement of matter distribution in the universe. As radio waves travel across space, any interstellar gas, or plasma, along the way can distort or disperse the wave's properties and trajectory. The degree to which a radio wave is dispersed can give clues to how much gas it passed through, and possibly to how much distance it has traveled from its source. The researchers also plan to use the bursts, and their dispersion estimates, to map the distribution of gas throughout the universe. An FRB detection machine, looking both far and near. Scientists are only beginning to explore the rich world of FRBs thanks to observations from CHIME. Having a large sample of FRBs unlocks countless possibilities. As one example, we are now in the era of using FRBs as cosmological probes, says Alex Josephi, a PhD student in physics at McGill. We can begin examining large-scale structures, clusters of thousands of galaxies. We can help map the distribution of cosmic dark matter and study the evolution of matter throughout our universe's history. Nearby FRBs, such as some of those described in this CHIME FRB catalog, are inarguably the best sources to test models of the origins and properties of FRBs, adds Mohit Bhardwaj, a PhD student in the McGill Physics Department. If we want to learn the most about FRBs, like if they shine in optical or X-ray light, nearby FRBs are our best options. As the telescope detects more FRBs, scientists hope to pin down more clearly exactly what kind of exotic phenomena could generate these ultra-bright, ultra-fast signals. About CHIME. CHIME comprises 4 massive cylindrical radio antennas, roughly the size and shape of snowboarding half-pipes, located at the Dominion Radio Astrophysical Observatory, operated by the National Research Council of Canada in British Columbia, Canada. CHIME is a stationary array, with no moving parts. The telescope receives radio signals each day from half of the sky as the Earth rotates. While most radio astronomy is done by swiveling a large dish to focus light from different parts of the sky, CHIME stares, motionless, at the sky, and focuses on incoming signals using a correlator, a powerful digital signaling processor that can work through huge amounts of data, at a rate of about 7 terabits per second, equivalent to a few % of the world's internet traffic.